what's incredible is you can go from screen to print.
That's right.
Very easily.
Yes.
Welcome to Talking Design and Engineering by MakeLab. Insights and advice from industry leaders driving innovation and shaping the future of people, processes, and technology in the world of physical products. So hi everyone, my name is Christina Perla and I am the host of Talking Design and Engineering by MakeLab. And so join us on our first episode as we discuss an amazing set of new capabilities and the collaboration between MakeLab and Inkbit. And with me now today is Davide Marini, the CEO of Inkbit. Welcome.
Thank you, Christina, for inviting me.
Yes,
Thank you.
Thanks for making the time. This is great.
Oh, you're welcome.
So to set the scene a little bit, a lot of listeners will know about FDM and SLA. They're very preliminary prototyping materials. They're very cost effective. They're great for early stage. A lot of the struggles with those materials as you bring that into functional prototyping can be about precision, accuracy, fitments, warping even. So what I'm very excited about is that VCJ is here, which really tackles all of that. And it's really great for that later stage functional prototyping. Super precise. The parts I'm still amazed with, I'm obsessed with. And what's interesting is this really caught our eye back at IMTS in 2022. So it's a huge show. The additive manufacturing corner was just a small corner of the whole floor, but Manny and I were walking it, and the Inkbit machine was on display. It was running. I think it was in demo mode, but it was running. We met the team. We saw the precision of the materials like we see here, and we were just pretty amazed. And so
thank you.
Manny and I reached out, started a conversation. Every time we dug deeper into the company, it really aligned with how we wanted to be as a company. We wanted to be a standout company with good morals, good ethics. We're not overhyping. We're delivering on good quality product and mission driven, and that's what we found with Inkbit.
Oh, thank you so much.
Yeah.
I'm glad that this resonates with you. Thank you.
It really, really does. And so let's dive into it. So
Great.
I always like to set the stage with, who are we? So tell me a little bit about yourself and how you got into this world of additive manufacturing.
Sure. My name is Davide Marini. I'm originally from Italy, as you can probably tell from my accent. I was born in a small village in the north part of Italy. My parents had a bakery, so I learned small business from a very early age. I was interested in how things work, so I graduated in engineering from Polytechnic of Milan, mechanical engineering. I obtained my MBA in France at Collège des Ingénieurs, and I started my career, of all places, in investment banking. So I was at JP Morgan on a trading floor in London. And I did this out of curiosity because a friend recommended that I consider the field. And I loved it because it was very hectic. In many ways, it reminded me of the bakery. But eventually, my soul gravitated more towards the application of engineering to real-world products. And so I decided to leave finance and go back to school. So I came to MIT here for my PhD in mechanical engineering with a focus on materials. And eventually I spent a few years in pure research at Harvard Medical School. I worked on nanomaterials for biological applications. And at that point, a friend invited me to consider entrepreneurship. So he invited me to start the company with him. He had invented a very beautiful technology to manufacture small hydrogel particles for biological applications using photopolymers. So this was, we didn't call it 3D printing, but it was in fact 3D printing. The company operated in the field of life sciences. We developed a multiplexed array for detection of microRNA. The company was eventually acquired by Abcam, a British company. And then I was looking for my next adventure, and I was introduced to the inventors of the technology that is now behind us when they were still working at MIT in a lab. So that's how I came into the field of 3D printing. So the company was spun out of MIT in 2017, And I didn't know anything about 3D printing.
Wow.
So that's how I came into this world.
I feel like that's a common thing amongst almost everyone I ask that's in this industry is, we didn't go to school for it. We
Yes.
kind of fell into it. We brought external knowledge from other industries into this to make it better,
Yes.
which is very cool. And so I also love to start off every episode with 3 main takeaways, just for the listener, tidbits. So what would you say are 3 main takeaways as to why VCJ should be on your radar?
Yeah, so VCJ is the technology that is at the heart of our company. It was developed at MIT. As you know, essentially it amounts to endowing a machine with a set of eyes. So very much like an artisan that can maybe check the progress of the work in real time. That's pretty much what the machine is doing as we speak. So every layer that is deposited, we scan it with a scanner so that the machine keeps comparing how the work is progressing. So I would say there are 3 main advantages. The technology is natively multi-material. So we chose material jetting as our foundational platform for VCJ. And this was intentional because my dream is to essentially enable designers, engineers, manufacturing companies to make full products. One day I really would like a technology that can create fully functioning products out of the machine with no assembly required. So that's where we're going. So the fact that it can create, even now, it can create fully functioning assemblies. The second reason I would say is precision. The fact that we have a vision system integrated into the machine makes the process very accurate, very repeatable, very precise. So let's say you want to print a product that comprises maybe hundreds of components, because we can pretty much print the CAD file directly of each of those parts, you have a guarantee that they will fit together properly. So precision is a very important advantage. And I would say the last advantage that I would mention, among others, is the yield. It's a very fast machine. You can see it in front of us. This is a very, very high density build. So you can print hundreds of parts. You can see it's multi-material. It's soft and rigid. Speed
and how long
yield.
did this take?
About 8 hours.
Wow.
Yeah.
That's...
Yes. The other advantage is that we use wax as a support material, so it can be easily melted away. So many things get confused by the struts that you see among those components and think that those are the support material, but we do this only for trade shows, otherwise it would fall apart. But the real support material that we use is wax, so it's melted away.
That's amazing.
Yes. The other advantage actually is that we recycle the wax, so it's a zero waste process. So the wax you melt away and then you reuse it. Yeah.
That's a standout all on its own. Waste is a very huge problem in additive.
That's right.
And so I really appreciate that. I think a lot of our listeners will as well.
Yes, no, thank you.
So where are we right now? What's behind us? Why are we wearing the safety goggles?
So we are now in the Inkbit, we call it the digital factory. So our business model is to sell machines and materials, but we keep open a small factory that we use to print sample parts for customers. So this is the digital factory. What you see behind us is our machine, the Vista printer, which I named because of the vision system. Vista is Italian for vision. So what you may not be aware of is that the machine actually comes with 2 parts. The one behind the machine itself is the material supply unit. So that comprises all the tanks of liquid polymers that we use in the process. Each tank holds about 80 liters of material, and the materials are fed from the top through those tubes into the main machine. So the whole system is designed for 24/7 operation.
Wow.
Also switching out the plate, you can just open this door and switch out the plate. It's a very, very easy system to operate. So we are at the Inkbit headquarters. We're in Medford, Massachusetts, in the Inkbit digital factory.
It's amazing because it's so clean.
Thank you. Yes, thank you.
It's so clean. It's so organized. It's a lot of what we try to do at MakeLab as well, but there are more machines behind us, probably not in frame, but it's just it's fairly quiet considering that there
Correct.
are so many machines and there's
Yes.
no spillage of, epoxy resins. It's
So the whole assembly is vented because we care about the safety of the employees, of course, and there is no powder. So the beauty of the system is that you don't have to deal with the powdering and with all the dust that can create. So it's a clean system. Yes, but that's why we designed it.
another
Yes.
thing that caught Manny and I's eye.
Yes, no, thank you.
It's the cleanliness.
Thank you.
So, okay, so we spoke a little bit about the VCJ technology, but can you go a little deeper into, how exactly it works? You mentioned that it scans after each layer.
Yes.
Talk a little bit more about that.
Yeah, so the idea of using feedback control for 3D printing was not new when we introduced it. Everybody desired that, everybody wanted that. In fact, my very first conversation with the inventors when I met them at MIT, and they described to me that in their machine there was a vision system that scanned every layer. And my first reaction was, wait, that doesn't exist already? Because I thought it would be, for an engineer, feedback control is the most natural thing that you can think of. So the difficulty actually was, how do you make it happen in real time? How do you design a system that scans each layer without wasting any time? So typically the trade-off that comes with precision is that you slow down the process, but we have a tremendous team of software engineers and optics engineers that design this tremendous vision system. So essentially the machine scans in real time, and a lot of the difficulty was really to develop the algorithms, the machine vision algorithms that can process data in real time. To give you a sense of the scale, the machine produces about 2 gigabits per second of data that need to be processed in real time. So after each layer is deposited, the system scans the entire layer, produces a 3-dimensional depth map of the system, and compares it to the CAD file, so that you can adjust in real time to how the process is developing.
Wow.
Yes.
And this is not a question we planned for, but I'm just very curious. How long did it take to go from, initial concept,
Oh, it's a great
an idea, to where we are today? I mean, or your first working model?
Yeah, so the very first concept was developed in a lab at MIT. And that was around 2016. The founders, the inventors invited me to join as CEO and to basically help them with the strategy, fundraising. So we spun out in 2017 with what I would call a very rudimentary initial prototype. And at the time, interestingly, we were actually not moving the plate. We were moving the print heads, very much like a polyjet machine.
Yes.
So there was an alternation between moving the print heads and then scanning. After my first round of funding, and plus significant funding from the Department of Defense, from DARPA, from the National Science Foundation, we developed what I would call the first large-scale format, which was similar in principle to what you see behind us, but larger and I would say more clunky. But the working principle was the same. We were moving the parts underneath the print modules. And that was really something that I really wanted, because I like the idea of a miniature assembly line where in the future I want to introduce new modules, maybe to potentially introduce parts that may not be 3D printed into the process. So I wanted an open system where the parts move underneath different stations. So it moves under the print modules, the UV light, the scanning system, and eventually some other modules that do more things to the machine. So anyway, that design was crystallized in around 2017, and I think we had the final commercial grade design, which you see behind you, around 2019, and we started shipping printers in I think it was 2021, something like
Wow.
that. So it took a long time.
That's an amazing journey, though.
It was very, very difficult. That one I can say. Developing this architecture was difficult, and especially making it work reliably. When you can just go home at night and it will just keep printing, and it's a very reliable machine.
Yeah.
Yeah.
I can tell.
Yeah,
After having printed quite a few parts, including the latest, the 500 Kobayashi cubes.
Oh, yes.
In a very short deadline for us.
Yes. This, for some reason, is the most successful part that we ever printed. Yes.
It's very eye-catching.
Yes.
It's very eye-catching and does a good job of being very interactive. But I can definitely attest to everything you said with. I did not also realize that you were really building the hardware to account for future additional modules.
Yes.
That's very interesting.
Yes. I cannot talk about the exact nature of what we are brewing, but something cool will eventually come.
Yeah.
Yes.
Can't wait to hear about it. So, okay. So this is quite a complex product for your first thing in additive.
Yes.
And so you mentioned a little bit about your previous company and how it used a lot of the same principles and concepts as AM, but on a very smaller microscopic scale. So, but have you had experience with other technologies at all?
In 3D printing?
Yes.
No. This is my first 3D printing company, and you are right in saying that this is very complex. And I often joke with my friends that Inkbit is really starting 3 companies in parallel, because what makes the machine work is a perfect concert between the chemistry of the materials, the hardware, the precision of the hardware, and the optics of the vision system and the software algorithms. All of those components need to work together in unison perfectly. So we need a chemistry team, we need a software team, we need an engineering team. It's a very complex system to bring to light. My previous company was much simpler in terms of underlying technology. It was a beautiful, elegant technology. In a sense, it was essentially 3D printing. What we did, we used a layer of PDMS to create basically an oxygen inhibition layer to be able to 3D print essentially acrylate. We didn't call it 3D printing, but it was basically using UV light with a photomask on top, and so that we could create encoded hydrogel microparticles embedded with DNA snippets that would basically for hybridization assays for the complementary microRNA. So it was conceptually similar. We still use UV light, photopolymers, and a way to structure the light. It was conceptually similar to what we do here.
That's very cool.
Yeah.
Very happenstance how you go from one to the other.
Yes.
That's very interesting. And so talk a little bit more about the 2 materials that are out today.
Yes. So one of the most interesting aspects of this process, VCJ, is that it is completely contactless. So there is no need for mechanical planarization. So because of this, we can open up the array of materials that we can print. So if you think about the history of photopolymers, essentially, if I had to make a crude generalization, they come pretty much from the coatings industry. They're mostly acrylates, and this is because it's a chemistry that works very well at being controlled very precisely in space and time. So if you turn off your UV light, the reaction should stop. So, but that also limits the type of chemistries that you can use. Because the process is contactless, there's no planarizer, there is no scraper in our machine, we can use, for example, dark cure chemistries. And one of the chemistries we use is epoxy, which is very common chemistries in manufacturing. So epoxy is a dark cure reaction. Once you shine the UV light, the reaction will start and you cannot stop it. So if you were to use epoxy into, for example, a traditional material jetting architecture, the epoxy would stick to the roller and jam the machine. So the fact that we have a vision system is key to using new chemistries that cannot be used in traditional material jetting. That's why this opens up a floodgates of new chemistries that we're working on. The first 2 sets are the epoxy. This is a tough epoxy that, approximately speaking, maybe not quite, but it's very similar to nylon 12. The other chemistry is a thiolene chemistry that we use for the soft elastomer. So that is a type of click chemistry, in essence, that gives us very, very good properties. Typically, customers are very impressed by when they see these parts, because it's very hard to make something like this, for example, an extremely delicate array of lattices at very high resolution in a soft material. That's very hard to make. So in this part, we try to showcase all our capabilities. Some of the customers that pick up the part at trade shows may not realize that there are secrets hidden into this. I can share some of them.
Please do.
So, for example, where you see these fins, this is actually a cage, and if you shake it, there is a little ball inside to show that we can print captive components. Of course, it's multi-material, so there's no assembly. This came out of the machine like this. The other thing is we can print barcodes, QR codes. So to showcase the precision, we can print threads. You can see it here. Something that some people may not have noticed is that there is a little bit of a nerd joke here. So this is a miniature benchy boat in a soft material that you're encouraged to find when you use this cube.
We usually ask people, we're like, did you find the benchy? And then they're trying to turn it.
That's right.
And they get to experience all of it.
That's right.
So there's so many different materials that you could have started out with. Like, what was the inspiration behind starting with these two?
The first material, the epoxy material, was developed as a material that back at MIT, actually, when essentially we looked at what's already used in industry beyond acrylates. So that was the first starting point. The soft material actually came from a collaboration with Johnson & Johnson. So Johnson & Johnson was an extremely important partner when we started the company. And so the soft material was destined to a personalized medical device. I cannot disclose the details of that project, but the inspiration for the soft was Johnson & Johnson.
Wow.
Yes.
Okay. And the tough epoxy?
The tough epoxy was I cannot tell you the exact details of that. It was because of a collaboration we had with a robotics company.
Gotcha.
They wanted a tougher version of the original epoxy material for applications in robotics where the products need to withstand impact. And
so that's very interesting because you started creating materials directly for a specific use case.
Yes,
which means you weren't just guessing. You were making something that was functional for a specific purpose.
Yes, that's what we try to do.
Yeah.
Sometimes it helps to have a generic material with cool properties and show it. But I think I believe in market pull, so we try to always develop things that we already know will be useful.
You want to be valuable, value add.
Yes, that's right. That's right.
To put it plainly.
Yes.
So in the context of industrial design and engineering, what are some tangible benefits that really play a part in prototyping, part quality, and functionality?
Of
We
VCJ.
discussed some stuff.
Yeah, so I would say the coolest thing I've seen, and I think this will be a trend that is here to stay for the entire manufacturing industry, is this idea of hardware-software co-development. So this came out of a collaboration. I mean, I learned about it. We didn't invent it. I learned of its importance through a collaboration with a robotics company. So typically, especially in robotics, where the iteration cycles need to be very, very fast, because it is clear to everybody that we need more and more automation. Typically, robotics engineers need to change the algorithms, the control strategies of the robots very frequently. And so software, we have come to expect, can be changed instantly and deployed instantly, very quickly. Nobody is surprised by that anymore. But we can't do that in manufacturing today. So my dream for Inkbit is to enable a new way to conceive and prototype and manufacture complex products such as robots. Because with our technology, you can actually have a rate of change of your hardware match the rate of change of your software. So for example, let's say I'm a designer of a drone, and all of a sudden I want to change the control strategy, the control algorithms of my of my drone. But in order to take advantage of this new control strategy, I need the frame to be slightly different. Or let's say I'm developing a robotic arm for picking groceries, for example, and I want a different control system, but I need a slightly different architecture of the hardware. With this machine, you can do it overnight. Let's say I want to completely redesign the robotic arm. You can print 500 components and you can have them the next morning. And you can put them together, so you can move your software iterations at the same speed as you're moving your hardware iterations. That's essentially what excites me very much about this technology.
And with the precision and the accuracy, and with the wax as the substrate for supports, you mentioned something earlier as we were preparing, and this leads kind of into the next question. But what's incredible is you can go from screen to print.
That's right.
Very easily.
Yes, that's right. So I like the idea of printing the CAD file directly. No need for tweaks or changes that are dependent on the process.
Yeah.
Just print the CAD file and you have it exactly as you saw it on the computer. That's my aspiration.
That's amazing.
Yeah, no, thank you.
It's truly amazing.
Thank you.
And so, on that note, precision usually comes with trade-offs, especially in the world of additive manufacturing. You have one thing that's revolutionary and you have to sacrifice something. You see this a lot with traditional technologies, and it could be print time and quality. If you want to go at a higher resolution, you want to print at a higher resolution, you're oftentimes extending your print times. So would you say that there are any trade-offs, per se, with the VCJ tech?
So, you're right. Typically, if I didn't know about this machine and I would advertise, okay, this is a far more accurate system because there is a vision system inside, the first thing I would think is, okay, it must be slower because you need the time to scan every layer. So that's why it took us several years to develop it, because we didn't want that compromise to be in effect. So the beauty of VCJ is that there is no slowdown. The speed is really dictated by the speed of jetting the droplets. So the scanning doesn't waste any time. And this is really thanks to the tremendous software and optics team that we have. They did a fantastic job in developing a system that can scan in real time. So there is no compromise in terms of speed. Of course, there is a compromise that is inherent in the nature of material jetting. So it essentially depends on the print head that you choose and on the droplet size. So we chose an intermediate, I would say, trade-off between high resolution and speed. But also the beauty of material jetting is actually its scalability, its modularity. If we wanted a far higher resolution, we just change the printhead. If you want a bigger machine, you can just add more printheads. So what I love about inkjet that maybe should be more advertised, I think, is the fact that it's very modular, it's very scalable, and it has already been proven to work at industrial scale in the 2D printing industry. Because think about how many books and posters and ceramic tiles are decorated by inkjet. Nobody questions that inkjet is scalable to industrial scale. So that's what I really like about this. Yeah.
Amazing. That's amazing. And I can really appreciate all the time and effort it went into, bringing this from 0 to 1,
Thank you, yes.
I'm involved in a lot of different hardware communities, and, a lot of who we spend time with professionally as industrial designers, and it's all about process.
Yes.
And one thing that, that you're saying that really resonates with me is quality.
Yes.
Quality first.
Yes.
You want to deliver a good product.
That's right.
I can really appreciate that.
That's right. And essentially, this is a machine, it's a process with an integrated inline process control. Yes. Yeah.
Wow. Incredible.
Especially for medical applications, I think it should resonate as well. Yeah.
And so much of what you said really has been the reaction of MakeLab clients who have, come in and felt the different samples that we have. This is not the only one we have. We have a lot of others, including multi-material, and people who have, customers who have really printed parts. There's been a lot of gasket printing. And
That's
so
right. Yes.
it's been incredible. We have switched materials to the VCJ
Oh, thank
technology
you.
and the
That's
soft
wonderful.
elastic.
Thank you.
It's something we recommend off the bat if we see that type of geometry.
Thank you so much.
But is there anything else you'd like to add that we didn't cover today?
Let me think. So I think I would like to add something more at the industry level.
Okay.
Because I see in recent months there's a lot of turmoil in the industry. There is a little bit of what I would call a little bit of deflated enthusiasm, let's call it this way. My recommendation was to keep the faith, because I think we are changing manufacturing, and manufacturing is a fundamental component of American productivity, of American, strategic leadership. So I think that we should be proud that we are building a revolution in manufacturing, and it's a long journey. This is not like building a software company. It's hard. Manufacturing is hard.
It's
so
very
we should keep
difficult.
that in mind. That
And what I love too is great tech inspires better manufacturing customer relationships, which
Yes,
is
yes,
notoriously difficult.
Yes, that's right.
And so a big part of what we want to strive for with MakeLab is reducing that friction and making it more pleasant of an experience,
Yes,
so you don't have
yes.
to pull out your hair, so to speak. And
Yeah.
so I can really appreciate that, good technology, value add technology that's reliable and consistent makes our jobs easier to fulfill that mission.
Wonderful.
So,
I'm really happy that you appreciate it. Thank
I
you.
really do. I'm not even, overdoing it. I truly
Thank
feel
you
this
so
way.
much.
So thank you so much for joining us today. Thank you, Davide,
You're
for your
welcome. Thank you.
time and joining us. This has been a great conversation. I learned a lot that I didn't know before, and I hope that our listeners did as well.
And thank you so much for inviting us. Thank you.
Yeah,
Thank
of
you.
course. Thanks for tuning in. Subscribe to Talking Design and Engineering on Apple Podcasts, Spotify, or YouTube, or follow MakeLab on social media for the latest in on-demand 3D printing services.